Hi, this is a video where I'm going to be covering mainly 5.4, which is gas stoichiometry, and 5.5, which is Dalton's law, partial pressure. But I do want to talk about the ideal gas law. The ideal gas law is pressure times volume equals moles times the ideal gas law constant times temperature. The R value is on our equation sheet. You can see that we're going to be using this R, and that R is what's really the unit is liters atmosphere over Kelvin mole. That's kind of telling me that, oh, my pressure needs to be in ATM, my volume has to be in liter, my temp is always in Kelvin. But that is derived really from the combined gas law, where you combine Charles, Boyle's, and Avogadro's law. Sometimes we put moles down here too to represent, there's Avogadro's law. But I'm not going to go over that derivation. Just know that we can use the ideal gas law if we are not necessarily changing a gas, like from a new temperature or a new volume, but this is more like, here's our gas, then we can calculate. STP is given again on your formula sheet. It is 0 Celsius, which is the same as 273.15 Kelvin, and 1 atmosphere pressure. So sometimes you'll be given problems where they say it's at STP and they won't necessarily tell you the pressure and the temp. You just have to assume those. Also notice the molar volume. So 1 mole of a gas, if it's a mole, it's going to take up 22.4 liters of space. And it has to be at 1 ATM, 0 Celsius. And again, that is also on our equation sheet right here. So I'm going to keep going. So, you can, I'm not going to go into this, but this is kind of the showing you the part of the derivation for the combined gas law to the ideal gas law. But let's start here with Dalton's law, partial pressure. So this is just saying, like, if you take, like, here I have a gas and I have another gas, if I combine them into the same container, the pressure of each of those gases are going to add together to give me the total pressure. We can also calculate the pressure, partial pressure, that's what this is, of a particular gas, by taking the total pressure of the mixture of gases and then multiply that by the mole fraction. And a mole fraction is just the number of moles of that gas divided by the total moles of gas in the container. So some of the, we'll do one problem in just a couple of minutes using the Dalton's law of partial pressure. Gas stoichiometry, if you remember our mole map in honors, we're not going to use it right now, but mole, we know we can go to particles using Avogadro's number. We can go to mass using molar mass. And then we can also go to the volume of a gas. If it's at STP, we can use, 1 mole is equal to 22.4 liters. Sometimes it's not at STP. We can still use gas stoichiometry whenever there's a chemical reaction. We can figure out the moles, and then we can go and plug into PV equals nRT, which is what I'm going to show you first. So this is just a derivation of how we got the number 22.4. If we put in the STP conditions of the temperature, the pressure, the ideal gas law constant, and then assume it's for 1 mole, we do get that molar volume. But let's do this problem. So you, if you're doing it with a note example sheet, I don't have the reaction written out. It's 2 moles of mercury 2 oxide, and this has a molar mass of 216.59 grams per mole. That will decompose if you heat it into mercury, the metal, and then oxygen gas. So my question is focusing in on the gas right now. So I know, I want to know the volume of this gas. I know the temperature is 30 degrees Celsius. And if I add my Kelvin temp to that, I will get 303.15 Kelvin. I'm not going to do sig figs. I'm just going to keep my numbers until the end. And then I'll do sig figs. You can assume that any temperature, once you add 273, ends up with 3 sig figs. So in this question, really we have 3, 3, and 3, so we should end with 3 sig figs. And then they're also telling me the pressure of the gas is 725 torr. So I want volume, so I really want to use PV equals nRT for oxygen, but I don't know the moles of oxygen. So I'm going to start with stoichiometry with my 4.10 grams of the mercury 2 oxide. I'm going to convert that into moles by using molar mass. And then I'm going to convert over using my mole ratio. So 1 mole of oxygen for every 2 moles of mercury 2 oxide. So when I do that, I'm going to get a number. Again, I'm going to hold it in my calculator. I'm rounding it on paper. So now I know my moles, and I have the other information about the oxygen. I've already converted my temperature, but I do need to convert my pressure. So in order to use the ideal gas law constant, my pressure has to be in ATM. So I would take 725 torr, and this is on my equation sheet. I know that 1 ATM is equal to 760 torr. So when I do that conversion, I get 0.9539. Again, I'm not rounding, I'm holding in my calculator. Now I'm finally ready to use PV equals nRT. I'm going to move this stuff, make this a little smaller. This was kind of all my side work, but I do want to show this work. But now I'm going to plug into the formula. So I know my pressure is 0.9539, the whole number, ATM. Volume is my X. My moles, again, I'm going to put the whole number in. And then I'm going to move this a little. Then I'm going to use my R value. And I'm going to put my unit in to show you how that can help. You know that you did it correctly. And then my temperature. So I would divide both sides by my pressure. So I know my volume equals this. And then I can put that in my calculator. I can also see that my moles cancel, my temperature Kelvin cancel, ATMs cancel, and I'm left with liter, which is a good sign that I did this correctly. So when I put all these numbers in, I should get a volume of 0.247 liters. Sometimes they'll ask for milliliters. It's just a simple multiplying by 1,000. So if they had asked, it would have been 247 milliliters. Next, I want to go over a way to use the ideal gas law with different variables. So we know that the ideal gas law is PV nRT, and we know this is mole. On my formula sheet, and plus we know this, moles always equal the mass in grams divided by the molar mass. The way we do it usually is we take our grams and we multiply by 1 mole over that molar mass, but really we're just taking our mass divided by the molar mass. So what I can do is I can substitute in this right here in place of the N for the mole. So I can say PV equals mass of the sample times R times T over molar mass. that's one way I can use the equation, and I will. Another thing I could do is, if I'm interested in density, if I have been given the density or I'm solving for density of a gas, I can take this equation and divide by volume on both sides. So I get, pressure equals mass times the ideal gas law times temperature over molar mass, remember that big M, it's not molarity, times volume. So density, and this is on your formula sheet, density equals mass over volume. So what I'm going to do is I'm looking and I see mass and volume here. So what I can do is I can substitute, instead of the mass and the volume, I can put density. So density times the ideal gas law times temperature over molar mass is also equal to P. And then I really can solve for any variable there, but there are problems that, and we're going to do one where we're trying to solve for molar mass. So we know that pressure equals density times R times T over molar mass. So if I multiply both sides by molar mass and then divide by P, molar mass would equal density times ideal gas law constant temperature and then divided by pressure. So we're going to do a problem like that right now. So in this question, I know I'm going to want to use some version of that because I know the density of the gas. This one is not a stoichiometry problem, even though it's under gas stoich, because it's not a reaction. So I know the density, and I'm writing it down wrong. That was the pressure. I'm given the pressure and the density. And I know the temperature is 27 Celsius. Add 273.15, and I get a temperature of 300.15 Kelvin. So in this question, I want to calculate molar mass. So again, I just did this previously. I'll do it again really quickly. PV equals nRT. We can substitute mass over molar mass for N, and then we'd still have the RT. We can then divide by divide by volume. And then I know pressure equals density times R times T over molar mass. And then lastly, I can rearrange, solve for molar mass. And that is what I'm going to use here. So just to show you on your formula sheet, those substituted variables are right here. So I'm going to now calculate molar mass of this gas by taking the density times ideal gas law times the temp over the pressure. So the density is 1.95 R. I'm going to do the whole unit. And then T. And then I'm going to divide by my pressure. So let me try to move that so you can see better. I'm going to bring it down. So this is going to give me molar mass. I can show you that the atmospheres cancel, Kelvin cancel, liters cancel, and I'm ending up with gram per mole, which is molar mass. When I do this, I get 32.0 grams per mole. So this is most likely oxygen. So let's do another problem. So now we're going to use the molar mass that we just, calculated. We're going to use that formula again. And we're given the empirical formula of a compound. We're going to be able to figure out the molar mass of the true molecular formula, and then we'll be able to figure out that multiplying factor to figure out the molecular formula. So in this question, they gave me the volume. I am going to want to convert that right away. So whenever I use any version of the PV-nRT, volume has to be in liters. My pressure is going to be converted into ATM. And again, I'm going to hold that in my calculator, but I'm going to write down some of the numbers. And then I know the mass. So, and then I also know R and temp. So I'm going to show you again, just in case you need it. I'm going to substitute in mass and molar mass for N. And then I'm going to divide by both sides by V. And then I'm going to take this and realize that's density. Actually, I'm not going to do that this time. I'm sorry. So this time, they did not give me the density, and they do not want the density. So I'm actually going to solve for molar mass. So molar mass is going to equal the mass in grams times the ideal gas law constant times temp over pressure times volume. So I'm going to sub in 0.8 grams, 0.08206, temperature, pressure, and volume. And again, you can see atmospheres, Kelvin, liters, all of those cancel, and I'm left over with grams per mole. So when I do this, I will get 96.9. You can keep more sig figs because it's not really about the value. It's about showing your work. And then we're going to figure out N, which remember that's not the mole, but the multiplying factor where you take the molar mass of the molecular formula and you divide it by the molar mass of the empirical formula. So we just calculated the top one. And then I'm going to divide by the molar mass of the empirical, which is going to be, 12.01, 1.008, 35.45. So I do get a molar mass of 48.468. That's what's going to go down here. And when I do that, I should get like 1.999. So it's really, it's about 2. So then ultimately the molecular formula is going to be CHCl, but times 2. And you do want to distribute that to each of the elements. So this would be our answer. One more problem. We talked about Dalton's law in the beginning, that the total pressure equals the partial pressure of all the gases added together. There's lots of different variations on these types of questions, but in this case, we know our mass of a gas, and we can figure out the partial pressure of the gas by using the ideal gas law constant. So I'm going to figure out the pressure of the hydrogen and I am going to substitute little m, big M, RT over V. Don't have to do that. If you want, you can take your 1 gram of hydrogen and convert to mole right away. But I'm going to do it this way just because we've been doing these substitutions. But if you did it the other way, like here, you would get 0.496 moles of hydrogen. And then similarly, you're going to do a problem with the helium. You would take your grams of helium, and essentially you're dividing by 4 because that's the molar mass, and you would get 0.250 moles of helium. But I'm going to do it this way. So the pressure of the hydrogen is going to equal 1 gram times R. Oh my gosh, I'm forgetting R. 206. Times T, so 27 plus 273.15 is going to give me 300.15 Kelvin. So that's just my little conversion on the side. And then I'm going to divide by the molar mass. This is hydrogen, so it's diatomic. And then the volume is 1 liter in the question. So again, I can see my grams cancel, my moles cancel, liters cancel, and Kelvin cancel. So I'm left with atmospheres. And then when I do this calculation, I get 12.2 atm. So that's the partial pressure of the hydrogens. You have to realize, there's hydrogens in this mixture exerting pressure, and that's the pressure of the hydrogen, but there's also helium. So now we have to do that same calculation for the helium. I'm going to use the mass of the helium times R times T over the molar mass of the helium times volume. But like I said, if you want to go up here and just calculate the moles and then sub in, you would be subbing into P equals nRT over V. But I'm going to do it all at once. So 1 gram. I'm going to do my R. And my temp, still the same. Then I'm going to divide by 4, because that's the molar mass of helium, times 1 liter. And when I do that, I get 6.15 atm. So that's the answer. They wanted the partial pressure of each gas. So that's the pressure of the hydrogen, the pressure of the helium. Sometimes they'll ask for the total pressure then. And you would take your each of the gases' pressures and add them up. So if we did do that, to 12.2 and 6.15, and then we would round with our sig figs to 18.4. So I hope that helped. If you have questions, don't hesitate to ask.